So now that we've defined what a Taylor polynomial is, we're going to move on to what's called a power series in general, and we'll start based on our Taylor polynomials. We can create from our Taylor polynomials what's called the full Taylor series if we allow the end value to go to infinity. So we allow infinitely many terms. So far, we've been using power series to approximate known functions. If we're going to claim that by letting n go to infinity, these power series are actually equal to the known functions, we have to be sure that our series converges. If our Taylor series doesn't converge, we of course cannot make that claim. Once we're sure it converges so we can make that claim, we'll also be looking in this section at defining kind of new functions using power series, and sometimes those new functions might turn out to be pretty familiar as well. Right? So let's talk now in general about the idea of a power series. A power series centered at A is the infinite series, as k goes from 0 to infinity, of some constant multiplier c sub k times x minus a to the k power. For Taylor series, we had a very specific formula for the c sub k's, right? That was the derivative over the k factorial. But in general, a power series can have any c sub k and be fine. We've just been looking at specific examples that were called Taylor series. The interval of convergence, I, is simply the set of values of x for which this power series converges. And the radius of convergence, r, is the distance from the center of the series to the boundary of the interval of convergence, or in other words, half the width of that interval. I think that'll make a lot more sense when we look at a couple of examples. So, given a power series, whether it's a Taylor series or some other power series, how do you find the interval and radius of convergence? We're going to rely on two convergence tests that we learned about back in Chapter 8, the ratio test and the root test. Remember our ratio test said set up this value r, which was the limit of a sub k plus 1 over a sub k. And as long as the absolute value of that limit was less than 1, we knew our series converged. So we're going to use that fact to help us determine some of these intervals of convergence. We also had a statement for the root test, right? We defined rho as the limit as k went to infinity of the kth root of a sub k. And again, as long as that absolute value was less than 1, we got convergence. So we're going to go back to using those two facts. Okay. Quick little note. Notice that both of these tests are inconclusive if the limit is equal to 1. So we are going to have to check the endpoints of our interval separately. And you'll see that in some of my examples. All right, let's take a look at this first one. I would like to know, what is the interval and radius of convergence for this power series? By the way, notice it is a power series. It's written in a little bit different form. But if I wrote it as 1 over 2k factorial times x minus 0 to the k, can you see that power series form? It's a constant multiplier times x minus 0 to the k. So this one happens to be centered at 0. All right, because of the factorial, probably my ratio test is going to be the way to go. So I'm going to say this converges if r, which is the limit as k goes to infinity, of the absolute value of a sub k plus 1. Take my term and just replace the k's with k plus 1's. So x to the k plus 1 over 2 times k plus 1 factorial divided by, and I'm going to do times the reciprocal, the a sub k itself when I take the reciprocal, 2k factorial over x to the k. And I need that to be less than 1 in order to get convergence. All right, let's start working on that limit. The x's are no problem. If I simply subtract the exponents, k plus 1 minus k, that's just going to give me x to the first on top. I'll just put that over 1 for now. These guys, I would have 2k factorial on the top. And on the bottom, inside the parentheses, that's really 2k plus 2. So when I do the factorial of 2k plus 2, it'd be 2k plus 2 times 2k plus 1 times 2k on down. So I can stop right there and make the rest of that 2k factorial. And again, I want that limit to be less than 1. I can divide out the 2k factorials. And what I have is my number x over 2k plus 2 times 2k plus 1 as k goes to infinity. Now notice that no matter what finite value for x I plug in there, since the denominator is going to go to infinity, what I'm really saying here is 0 is less than 1. And that's true for any finite number x. So because of that, my interval of convergence I this time goes from negative infinity to infinity. Anything in between the infinities, any finite value of x, is going to give me an r value less than 1, is going to make this power series converge. The radius of infinity, half the length of an infinite interval is still infinite, so there's the I and the r. Okay. This one basically, what we're saying is converges all the time for any value of x. Let's try another one. In example 2, here's my series. And again, I won't write it out this time, but you can recognize the power series, right? The constant multiplier would be 1 over 2 to the k plus 1 times the x minus 3 to the k. So there's that power series. Notice that it's centered this time at x equals 3. That's our a value, if you will. All right. I'm going to go ahead and I'm going to really do this one the same way. Although I don't have any factorials, with the different k values in the top and the bottom, I'm not loving the idea of a root test, although I might be able to make one work. But I think I'm going to go ahead and do the ratio test again. Probably would work either way. I need, for convergence, my r, which is the limit as k goes to infinity of the absolute value, the a k plus 1. I replace my k's with k plus 1s. So I would have x minus 3 to the k plus 1 over 2 to the k plus 1, if you will. And then I'm dividing by the a sub k. Again, I'll just multiply by the reciprocal. So that would be 2 to the k plus 1 over x minus 3 to the k. And I need that to be less than 1. All right. These guys, I could just subtract the exponents. So that's going to give me x minus 3 to the first on top. And then basically the same thing here. If I subtract the exponents, the k minus 1s would cancel, and I'd have 2 to the first on the bottom. So there are no longer any k's in this expression at all, so I can drop the limit. That just says x minus 3 over 2 in absolute value is less than 1, meaning it's actually between -1 and +1. If I multiply by the 2, -2 is less than x minus 3 is less than 2. And if I add the 3, 1 is less than x is less than 5. So that's almost going to be my interval of convergence from 1 to 5. This time, though, because I didn't get any infinities, I need to test my endpoints. I need to check and see if 1 and 5 actually work, because those would have made the r equal to 1. And that's the inconclusive case. So I'm just going to kind of do that off to the side here. Let's start with the first endpoint, x equals 1. If x equals 1, I'm going to rewrite the original series just plugging in x equals 1. And I would get the sum as k goes from 1 to infinity of 1 minus 3, that would be -2 to the k, over 2 to the k plus 1. And I could separate that numerator out just a little bit. I could make that -1 to the k times 2 to the k over 2 to the k plus 1. And let's see, I can now have -1 to the k on top, and subtracting those exponents, that just gives me 2 on the bottom. So this is an alternating series, right? Just 1, -1, 1, -1, and so on. So really what I've got here is an alternating series with an a sub k of 1/2. Since 1/2 is not 0, that diverges by the alternating series test. So now I know that 1 is not in the interval of convergence. So I'm going to go ahead and say for my I, definitely a parenthesis on the 1. I have to check the 5 as well. So let's test x equals 5. Run out of space, so I'll take a couple shortcuts here. If I again go back to my original series and plug in 5 for x, that's just going to make the top 2 to the k. Over 2 to the k plus 1. And actually that one's going to simplify really easily. I can subtract the exponents, and that's just the sum of 1/2. So it's literally adding 1/2 plus 1/2 plus 1/2 plus 1/2 forever. That clearly diverges. But I could also say that since the a sub k's are equal to 1/2, which is not 0, this diverges by the divergence test. So that means that 5 is also not included. As far as the radius of convergence is the distance from the center to the edges. So remember the center was at 3. From 3 to 1 or from 3 to 5 is 2 units. So the radius of convergence is going to be 2. Another really easy way to get that is just find the length of the interval, 5 minus 1, and cut it in half. So 4 divided by 2 is 2. So there's my interval and radius of convergence. All right, let's do one more like that. In example 3, here's my power series. From 1 to infinity, I've got the x minus 5 to the k, and the coefficient, the c sub k, is 1 over k this time. Center, notice, is at a equal 5. Once again, my goal is to find the interval and radius of that power series. I personally, honestly, I use the ratio test about 99% of the time on these, so I'm going to go ahead and use the ratio test again. I'm going to say, let's define our r as the limit as k goes to infinity. Absolute value of, first the a sub k plus 1. So replacing the k's with k plus 1's. Divided by a sub k, or multiplied by the reciprocal of a sub k. Looks like that. And that has to be less than 1. All right. I'm going to have the fraction k over k plus 1 times, when I subtract these exponents, I would just get an x minus 5 to the first power on top. All right. As k goes to infinity, we could do a little L'Hopital's rule here. And that derivative here would be 1 over 1 times x minus 5 to the first. Absolute value is less than 1. So x minus 5 has to be between negative 1 and positive 1. And adding the 5, x is between 4 and 6. So that's almost my interval of convergence, but just like last time, this test would be inconclusive at the endpoints if it was equal to 1. And so I don't know yet whether to include the 4 or the 6. So let's test. Try x equals 4. If I go back to the original series and I plug in x equals 4, my series now becomes 4 minus 5 would give me negative 1 to the k over k. Notice this is an alternating series. The a sub k this time would just be 1 over k, the part that doesn't alternate. And that does go to 0 as k goes to infinity, right? K is infinity, that's going to go to 0. So this converges by the alternating series test. So when I go to write I, I'm going to include the 4. Let's test x equals 6. Again, when I go to write my series, I'm just going to plug the x equals 6 in. So I'd have 6 minus 5, or 1 to the k power, over k. Of course, 1 to any power is still 1. So that's just 1 to the k. And that's the harmonic series, which we know diverges. So the 6 does not get included. So my interval of convergence, 4 inclusive to 6 not inclusive. And my radius, again, if I just kind of find the length of the interval, 6 minus 4, and cut it in half, 2 over 2 would be 1. All right, let's do, actually, there is one more. I thought that was the last one. We have one more example of this. Example 4 here. Here's my power series. Notice this one is centered at 0. This is x minus 0 to the k. And the series is k factorial times x to the k. I'd like to find the interval and radius of convergence for f. So same deal. I'm going to start by putting in my r, which is the limit as k goes to infinity. Absolute value of a sub k plus 1, that would be k plus 1 factorial, x to the k plus 1, divided by a sub k, k factorial, x to the k, and I need that to be less than 1. So let's see here. K plus 1 factorial, I could write that as k plus 1 times k on down, or times k factorial, over this k factorial, which will cancel nicely. And then I can just subtract the powers on the x's, so that'll just become x on top. So I have the limit as k goes to infinity of the absolute value of k plus 1 times x. Has to be less than 1. Of course, as k plus 1 goes to infinity, this becomes infinity times x, which is almost always infinity. We'll come back to that almost always in a moment. And of course, infinity is not less than 1. So there's no interval of convergence. This thing diverges almost everywhere. When I say almost, there's one thing that we have to check. There are no real endpoints here. But what's the only x value for which infinity times x is not equal to infinity? It's x equals 0, right? If x equals 0, I would have an indeterminate form. So I'm going to note here that I need to treat x equals 0 as a separate case, since infinity times 0 is indeterminate form. And I'll do that right over here. So if x equals 0, again, go back to the original series and just plug in 0. We'd have k factorial times 0 to the k. Of course, 0 times k factorial is just going to be 0. So you end up adding up 0 plus 0 plus 0 plus 0, which gives you 0, and it converges, not very interestingly, but it converges to 0. So there's no real interval of convergence. We're going to say this series converges only for x equals 0. And our radius of convergence would be 0, since we're not going anywhere with that. All right, so that is calculating radius and interval of convergence. Again, it just tells you what x values you are allowed to use if you want your series to converge. So just to clarify one more time, for example on this one, back in example 2, if I want my series to converge, I could only use x values between 1 and 5. If I were to use 6 or 7 here, this would diverge. For this one, if I want my series to converge, I'm only allowed to use x values between 4 and 6. Otherwise, that will diverge. That's what that's saying to us. All right. The next part of this section talks about combining power series. Functions that are defined as power series can be combined with one another using a lot of just the normal rules of algebra. Remember, a series is nothing more than a sum of a whole bunch of terms. It's a polynomial, right? And so all the stuff you can do with polynomials, you can do with series. You can add and subtract them, right? So if I've got a power series of c sub x or c sub k's plus d sub k's, it's going to converge to f plus or minus g on the interval. Sorry, I should have started up here. If I've got my two power series, which converge to f and g respectively, then the sum of them converges to f plus g, and the difference converges to f minus g. In other words, you can add and subtract power series. You can multiply by a power of x. So if I take x to the m power times a power series, I could literally take that x to the m and distribute it to all the terms. And of course, all that's going to do is add m to every exponent. Composition. If I've got h of x equals, notice this is a power, b times x to the m, then I can take the composition of the power series, h of x to the k, and it converges to the original function composition of f with h. We're going to look at an example of each one of those, and I do think that they are a little more obvious when you look at the examples. Now, in order to practice using those, it's actually really helpful to us to have a list of kind of known or given power series for several elementary functions. So the list is actually on the next page. Shows us some Maclaurin series, that is the ones centered at x equals 0, for a number of different common functions. A couple of them you're going to recognize as ones we've already done, or that maybe you did in your homework. And in any case, for the rest of the problems that we do for the rest of the section, we're just going to accept them as givens that we can use. Okay. So here is my given list of Maclaurin series. A couple of them I'll point out to you. Here's one that we did together, right? Here's e to the x. Recognize that one? Right? We did that one. And we did sine x as well. So there are a couple here that we did. They might be in slightly different versions. I think I happen to have chosen to do 2k minus 1 instead of 2k plus 1 to make my series, but they both result in odd numbers. So it's the same idea. The rest of these, again, whether we've done them or not, we're now going to just accept them. These are givens, and we can use them. So, in example 5, we're asked to find a power series representation for each function, and then to find the interval of convergence. So my function is x cubed over 1 plus x. And the first thing I'm going to do is kind of tear that apart and say that would be x cubed times 1 over 1 plus x. And the good news is 1 over 1 plus x up here, right there, is one of my known series. So I'm just going to replace the 1 over 1 plus x with this. So x cubed times 1 over 1 plus x was the sum as k goes from 0 to infinity of negative 1 to the k times x to the k. And you'll notice they list the interval of convergence here. That's valid for the absolute value of x less than 1. So I'm going to have to include that as well. So you can see, because the interval of convergence is already given, we're not going to have to work very hard for it. All right. To finish, when we write this as a power series, we really don't want something out in front. So I'm going to literally multiply this x cubed in here times the x to the k. And so I'm going to have negative 1 to the k times x to the k plus 3. The interval of convergence, I'm just going to borrow from this, but I'll write it as an interval like we were. The absolute value of x is less than 1. Or in other words, I goes from negative 1 to 1. I guess we weren't asked, but if we wanted to, we could say the radius of convergence is 1 there as well. And that's it. All right, let's try a couple more. Can't all be that easy, right? We can only hope. Here's our next one. We've got the natural log of 1 plus x over 1 minus x. And the first thing that jumps out at me when I look at that is it would be really nice to use one of my log rules from algebra to split that up. And let's write it as the natural log of 1 plus x minus the natural log of 1 minus x. Okay, so just basic algebra there. The good news about that is both of those are listed right here as given series. So I'm just going to copy this for ln x plus 1 and that for minus ln 1 minus x. So I've got the ln of 1 plus x, again just copying from the table, is the sum as k goes from 1 to infinity of negative 1 to the k plus 1 times x to the k over k, plus, again, that minus sign was actually already part of it, so I don't even have to include it, right? The minus sign's already here, so I'm just going to copy this one right from the table. And that one was the sum as k goes from 1 to infinity of x to the k over k. All right, let's talk about the intervals of convergence real quick before we talk about simplifying this. The first one, the ln 1 plus x, that converged from negative 1 to 1, including the positive 1. And the second one, the minus ln 1 minus x, that one converged for negative 1 to 1, but including the negative 1. When you are combining power series, you can only use x values in your radius or your interval of convergence that belong to both of these, the intersection of these two. So what I'm going to have to say is I'll have to keep my x's strictly between negative 1 and 1, because negative 1 doesn't work for that one, and positive 1 doesn't work for that one. So already I can see my I goes from negative 1 to 1, and R is 1 if we care. So that part's already done. All right, so let's now talk more about that series. I can combine them. And actually, you know what? I'm going to do something. They have a common denominator, so I can certainly put them together over one common denominator, k. And I could actually even factor out the x to the k, couldn't I? So this would be a negative 1 to the k plus 1, and then just plus 1, all times the x to the k. I don't know why I put a 4 there. Okay. Stare at that for just a moment, because I did kind of a lot of algebra in one step there. I combined these two series, kept the common denominator of k, and then in the numerator, I factored out the x to the k, leaving the negative 1 to the k plus 1 in the first one, and then when I factor out the x to the k, that was just a plus 1 in the second one. I'm going to start listing terms, starting by writing out the k equal 1 term and so on, because I think we're going to be able to see a pattern pretty quickly. When k is 1, I would have negative 1 squared plus 1, x to the first over 1. When k is 2, that'd be negative 1 to the 2 plus 1, or 3, plus 1, x squared over 2. Go a little further. We're up to k equal 3, so that would make that negative 1 to the 4th plus 1, x cubed over 3. And we're up to k equal 4, so that'll make that a 5th power. So the 4th over 4. I'm going to write out one last one. I'm now up to k of 5, so that'll make that negative 1 to the 6th plus 1, x to the 5th over 5, and so on. What I want you to notice is that half of these terms go away, right? This first one is going to be a 1 plus 1, or 2x. But the second one, negative 1 plus 1, is going to give us a 0 on that one. This one will be a positive 1 plus 1, or 2x cubed over 3. This one's a negative 1 plus 1 is 0 again. Here we got 1 plus 1, or 2, and that'll be x to the 5th over 5, and so on. And so, again, I think there's a pretty clear pattern here. I could make this x to the 1st over 1 just to emphasize it. It looks like we're going to get the odd powers divided by those same odd numbers. And then, of course, every term will be multiplied by 2. So, if I wanted to write this kind of nicely as a series, I could say, let's let k go from 1 to infinity. And every term is going to have a 2 on the top, and then x to an odd power. I'm going to do the odd powers just like I did before. 2k would be even, 2k minus 1 will be odd. And the denominator is that same odd number, so divided by 2k minus 1. So there's my series, and we already did the interval and radius of convergence. All right, so let's see, that was multiplying a series by a power of x was the first example. This was, in this case, subtracting a series or two series. This last one is going to be the composition example. I'd like to find a series, a power series for f of x, which is the cosine of 3x. Now, we don't have on our list the cosine of 3x, but we do have a series for cosine x. It's right here. I'm going to write down this series form right now. And note that this converges for all x values, anything absolute value of x less than infinity, or in other words, from negative infinity to infinity. So I'm just going to copy down this series. Cosine of x is the sum as k goes from 0 to infinity of negative 1 to the k times x to the 2k over 2k factorial. By the way, notice that just like the sine had all odd terms, notice the cosine has all evens, right? These are all going to result in even powers on the x and even numbers in the denominator. If you remember your geometry, a little bit of those functions, when we graphed the sine function, it was an odd power, it was an odd function. And when we graphed the cosine, it was an even function, right? The symmetry was with respect to the y-axis. So those ideas of odd and even functions are really playing out with the odd and even powers in the infinite series. And again, this was for all x, absolute value x less than infinity. So in other words, well actually, hold off on that for a minute. All right, we want the cosine of 3x. So we're literally going to take the x from the original series and do a composition. We're going to replace the x with a 3x. Now there's not a lot I could really do to simplify that, so that really is my series. I'm done with that part. But I should talk for a moment about interval of convergence. Because the original interval was infinite, actually the infinite interval will be maintained here. But here's what you have to be careful of. Because I replaced the x with a 3x right here, I have to do the same thing with the interval of convergence. I have to replace that x with a 3x. So this really says the absolute value of 3x is less than infinity. Now in this case, because dividing infinity by 3, it still stays as infinity. It doesn't change the interval of convergence. But if I had done this type of problem, where the interval of convergence maybe was something like the absolute value of x less than 1, when I divided by 3, it would have changed my interval. So watch out for that. I think we're actually going to see that in an example here a little bit later in this section. So in this case, I'll say my interval of convergence really does go from negative infinity to infinity, and r is infinity. All right, let's pause right there. This is getting a little lengthy anyway, and then we're going to do a little bit of calculus with power series to finish out this section in the next video.